I'm back. Change my hat. It's a Christmas tree with Mickey Mouse on it. There's Mickey right there. Okay, back to acids and bases. All right, we just did recap. Remember, base, acid, right? The base is going to take that hydrogen. Yes? Okay. A Bronsted-Lowry base must have a lone pair of electrons to accept the hydrogen. That's what makes it a base. Not everything can be a base. You have to have a pair of electrons to accept it. So if you look here at water plus hydrochloric acid is our acid here. Water's going to act as the base here. There's got to be some place to put it. What they do here is add some space. So here, this hydrogen is going to pop off and come over here. Watch, look at that. Now it's got 3 hydrogens, still space for these electrons here, and the chlorine is minus. It's missing one right there where the hydrogen used to be. Does that make some kind of sense? Not everything can be a base. You have to have this electron, a pair of electrons to accept that hydrogen. Okay. Mark down questions. We're going to go over this in lab. I just want to get the base lecture out of the way so that we can really work through things. Okay. A base can either be neutral or negatively charged. It can be positively charged. It has to be neutral or negatively charged. If the base is neutral, the product has a positive charge. So if the base has no charge, the overall product is going to have a positive charge. Even if it is positive, it's still going to keep the positive charge. But that sometimes confuses people, that the base starts out with no charge at all and then it becomes positive. It's just gaining that hydrogen ion. The product of an acid-base reaction can also behave as an acid and base. So what that means, settle down. I know you're panicking about that. Settle down. It just means that it's reversible. It just means that the base can also, it can reverse it, and the conjugate base can flip it back over. Does that make sense? It can just give the hydrogen back. It can be like, hey, you know what? Didn't need the hydrogen anyway? Why don't you take it? Become an acid again. Good luck to you. So they're just reversible. Don't panic about it. Just trust me. Reversible, it's all fine. Okay. Pairs of chemical species, such as the bases and bases with their hydrogen ion on them, are called conjugate acid-base pairs. So in this group of awesomeness, this is basically what we're going to be doing in lab. You're going to identify the base, you're going to identify the acid, then you're going to identify the conjugate acid. So it started out as a base, then it took the hydrogen ion, right? Boom, now it's an acid. All right, started out as an acid, now it's a base because it doesn't have a hydrogen ion. Can't be an acid without a hydrogen ion. They're found on opposite sides of the chemical reaction with formulas that differ by 1 hydrogen ion. That's how you identify them. Look at this. NH4. NH3 over here. I bet that's the base. See how it works? H3O, H2 over here. There's the base. Okay? These are the conjugate acids. They're going to give up this hydrogen ion. These are the bases. They're going to, they are the ones that also gave up. They're going to get, does that make sense? So it starts over here as the acid. You have the hydrogen ion. They have the hydrogen ion over here. It gives it up. Here's the hydrogen ion plus this. Does that make sense? Okay. We'll work on it, I promise you. Here's some examples. Again. Conjugate acid, NH4. Conjugate base, NH3+. Then there's a hydrogen ion there. Does that make sense? Okay. Strong acids. So we have degrees of these things. Strong acids, really nasty. Don't drink them, it'll kill you. Strong acids, they give up protons easily and are 100% associated in water. So here is our strong acid. It gives up a proton easily. So here is the strong acid. There's the proton. It's given that thing up, and it's just got the negative ions. There's no real acid left. A weak acid is still holding on to that proton. I'm not sure I'm ready to give that up. I think I'll just keep it. Strong acid, weak acid. Did I just do strong acid? Weak acid. There we go. A weak acid gives up the proton with difficulty and are substantially less than 100% dissociated in water. So here's our weak acid. It still has its proton attached. Here's the strong acid. It doesn't have the proton attached. Can you see the difference there? It's going to be the same with bases when we get there. Okay, that's not working. Okay, weak bases. Weak bases have a little affinity for the proton. You want to give me that proton? I don't really want it. I'm good. Thanks. It's like I don't want your sandwich. I don't want whatever you're giving out. I don't want it. I don't want your flyer. You just keep it. Just keep your hydrogen ion. I'm good. So a weak base isn't like give me hydrogen, give me hydrogen. It's like I don't really need it. I'm all set. Little affinity for the proton. Strong bases grab and hold on to the proton tightly. They're like proton. It's mine. Don't touch it. So it's harder to get it back. In a reversible reaction, you're going to try and get that hydrogen ion back from a strong base. Good luck. But if a weak base has it, it's like, you can have it. I don't really want it anyway. Do you see the difference? So as we do different reactions, you'll see the difference between a strong base and a strong acid and a weak base. Some strong acids. Hydrochloric acid. Pretty strong stuff. You put it in water, it dissociates into the hydrogen ion and to the chlorine ion. Weak acid, it would give that back if you needed it. It's not really that attached to it. It gave it up, but probably in a solution, half of them would still look like this. Strong base, NaOH. This is a super strong base. It takes on that OH really quickly. It pops. It's like, give it to me. Just give it to me. It's going to be hard to get that thing back. The weak bases, again, it's just, yeah, I'll take it, but it's not really that excited about it. Okay, here's some, just a table of weak bases and strong bases if it comes up in a sapling learning or in lab. It's in your book. There's an in-reverse relationship between acid strength and base strength. So if you have a super strong, so here's your really strong hydrochloric acid. Its conjugate pair is chlorine. The base is, if it's a strong base, then its conjugate base is the acid. The stronger the acid, the weaker its conjugate base. So it's like the really pushy person who's like, you will take this hydrogen ion. And the base is like, I don't want to. I don't really. Yes, you will. But I don't. Yes, you will. So it's like that. And it's the same. The weaker the acid, the stronger the conjugate base. The base is like, dude, you better give me that hydrogen. And the acid's like, okay. Fine. But can you imagine if you had a really strong base and a really strong acid, things would go bad. You have two strong personalities. Somebody needs to be willing to just give it up, and someone needs to really want it in order for this thing to work. Okay. Base strength. Okay, too much or not enough. This is just a little ditty here for your enjoyment. The major components of gastric fluids are hydrochloric acid. It's really low pH, about 2 in your stomach. The stomach is essential for digestion. So two things happen. You can have too much acid in your stomach. Your pH can be too high, and that can creep up through your esophagus and give you indigestion right here. Very painful. You take a base. You look at what is in Zantac or in Pepcid or some of that stuff. You put one of those in your mouth, and it dissolves. It acts as a base, and it takes the acid and makes it more neutral, and then the pain of the acid eating away at your esophagus goes away. The opposite thing can also happen, though. You can also have a system where the pH in your stomach gets too low and it doesn't actually dissolve your food. It's gross. It's like, instead of being 2, which just melts your food, your pH is like 4 or 5, and your food's like just sitting there. It's not getting dissolved. It's not doing anything. And it makes your stomach hurt, and it kind of comes back up because it's not actually being digested. And so you feel full. A lot of that time, it's like you feel full all day. It's like, I feel like my food isn't digesting. Your pH is probably actually too high. You don't have that good hydrochloric acid happening. And then what happens is people just exacerbate the problem. So they start popping Tums, which just makes your pH increase and increase and increase until your pH is like 5 and your food is just sitting there going, yeah, I've been here a couple days. I just can't get digested. So very often you need to figure out what's going on. If you think that's you can actually take vinegar, raw, it's like a raw vinegar, apple vinegar. They sell it most everywhere. And if you take that before you eat, it'll start acidifying your stomach, and you'll be like, oh, I actually feel like my food's digesting. So there's 2 different ways that works. But the major component of gastric juices is hydrochloric acid. Okay, I'll see you in a minute.